Line L1 has equation as shown where lambda is a scalar parameter. Just want to remind you, we've got a position vector, and then this -2, 0 is getting us onto the line. And then it's this 3, 0, 1 that's our direction vector. It gets you anywhere you want along this line. So let's say I went to there. My overall position vector would be here. It would be on the line. So here I've got 3, 0, 1, and I'm timesing by a parameter because I might want to go further. I could go in the opposite direction. I could go over here, and then my position vector would be here. We're told that L2 is then parallel to 1, 2, minus 3, so that would be another line, in fact. I've got some other vector, not sure what it is because it's not telling me, but then I'd be going along this line. But we're told, yeah, so here I've got 1, 2, minus 3, some scalar multiple of that. Maybe I call it mu, and I don't know what this one is, but that's kind of what's happening here. But we're asked to show that L1 and L2 are perpendicular. So for this, I can investigate the angle that they meet at. Now the dot product is given by A dot B equals the modulus of A B cos theta, where theta is the angle in between. And we've also got the version where you multiply the components. Not going to show where this comes from. Make sure you got both of them ready to use. Because if we can show the dot product is equal to 0, then the only thing that can be the case if both vectors are non-zero is that cos theta is 0 and therefore theta is 90. That's how we show they're perpendicular. So 3, 0, 1 dotted with 1, 2, minus 3 is equal to 3 minus 3 equals to 0. This implies cos theta is 0, theta is 90 degrees, and therefore 3, 3, 0, 1, let me do that again, 1, 2, minus 3 are perpendicular. So L1 and L2 are perpendicular. All about the direction vectors at the end of it. B, we're asked to determine a Cartesian equation of pi, where we're told this plane pi contains the line L1 and is perpendicular to 1, 2, minus 3. So let's get a sketch down the plane, and we've got the origin here. So we're getting onto the plane now using this minus 2, 2, 0, and then we're going, along this line. This is going to be L1. I've got the vector 3, 0, 1, or some multiple of it. Then told that the 1, 2, minus 3 is perpendicular, so that actually becomes my normal to the plane. I'm going to say n is equal to 1, 2, minus 3. So we know from before that, well, we know that this is the case, and therefore lambda times 3, 0, 1 dotted with 1, 2, minus 3 is also 0. But what I can do now is replace this by r minus 2, 2, 0. So therefore x, y, z minus 2, 2, 0 dotted with 1, 2, minus 3 is equal to 0. And therefore x, y, z dotted with 1, 2, minus 3 is equal to minus 2, 2, 0 dotted with 1, 2, minus 3. Just rearranged it. By the way, this is me essentially deriving r dot n equals a dot n, where r is the vector x, y, z, n is the normal in both cases, and a is the vector that gets you onto the plane. Here, I haven't, you could just use that straight away. X, y, z dotted with n, which is our 1, 2, minus 3, and then it's the -2 to 0 as A dotted with N. I've just kind of tried to derive it and show where it's come from instead, but you can go straight there if you prefer. So then I've got x plus 2y minus 3z is going to equal -2 plus 4 is going to equal 2. And this is the Cartesian equation of our plane. Above here, we've actually got what we'd say is the vector form for the plane. In C, we're asked to verify that A311 lies on pi. So when x equals 3, y equals 1, and z equals 1, the left-hand side of, let's call it star, is going to equal 3 plus 2 minus 3 is going to equal 2, which is the right-hand side. So equation satisfied. And therefore A311 lies on pi. Finally, we're given that the point of intersection of the plane in L2 has coordinates 2, 3, 2. Actually, what this really is just telling us how we can get onto L2, because remember at the start we just had that the L2 was parallel to it. So now I can actually write down the equation of L2. R is going to equal 2, 3, 2, the position vector to get onto the line, plus some scalar multiple, I'm going to use mu instead of lambda, times by that vector 1, 2, minus 3. And therefore, because I know that P lies on it, I can say that PQR is then equal to, and I'm going to bring it together, 2 plus mu, 3 plus 2 mu, and 2 minus 3 mu. There we go, there's our B. We're told the distance AB is 2 root 5. So actually, remember, this is actually OB. Therefore, AB is going to be OB minus OA. That was meant to be a minus. Which is then going to be 2 plus mu, 3 plus 2 mu, 2 minus 3 mu, minus 3, 1, 1. Which is mu minus 1, 2 mu plus 2, and 1 minus 3 mu. Now I know the distance is 2 root 5, so I can just find the magnitude of this vector. So it's 2 root 5. In fact, I can just square the 2 root 5 and use 3D Pythagoras. It's going to be mu minus 1 squared plus 2 mu plus 2 all squared plus 1 minus 3 mu all squared. And I've created a quadratic to solve. This ends up being, well, 2 squared is 4, root 5 squared is 5, so 20 is equal to mu squared minus 2 mu plus 1 plus 4 mu squared plus 8 mu plus 4 plus 9 mu squared minus 6 mu plus 1. Okay, this gives me 14 mu squared. Actually, these cancel out, don't they? So there's no mu term, but I'm going to get 6 here, so plus 6. Therefore, 14 mu squared is going to be 14, and mu squared is going to be 1, so mu is equal to plus or minus 1. Now, told that P, Q, and R are positive integers, so now we just need to check whether they are in fact are. So let's go with mu equals 1. Then we're going to get B as 3, 5, but then minus 1. So I'm going to reject it. It's actually going to be mu is minus 1 that I think is going to work out. Then I'll get 2 minus 1, 1. 3 minus 2, 1, and 2 plus 3. Our final answer is B115. Well done.